This is Chem Activity number 5, part 3. Now that we've established in question number 4 that the difference in boiling point between pentane and butane-1-ol cannot be explained by differences in London dispersion forces, we need to look at dipole-dipole forces and hydrogen bonding. Let us take a look at the information that's found at the bottom of page 22. Here we have electron density plots for the molecule acetone. So I've drawn two acetone molecules so that we can highlight the intermolecular forces between these acetone molecules. Now remember that the London dispersion forces are ubiquitous. So there are London dispersion forces holding these acetone molecules together. But the energy distribution plots also show that there's a degree of polarity in this molecule. Now of course we would have expected that as well, based on considering bond polarity, molecular geometry, and we also saw on a previous page the dipole moment for acetone being considerably high. Now the red part of the diagram represents an electron-rich region, and the blue part represents an electron-poor region. Now what I'm going to do is on the side here, I'm going to sketch, using bond line drawings, the acetone molecule as well. And as we know, we've got a very polar bond between this carbon, so delta positive and delta negative, and there is a molecular dipole in the direction of the oxygen. Note I'm skipping drawing the bond dipole, which actually runs essentially parallel to the molecular dipole. Now I can draw in a second acetone molecule here, and where we've got a delta positive and a delta negative, and the molecular dipole. And what we would expect is that there would be an attraction between the negative side of the acetone molecule and the positive side. Of course, these are only partial charges due to the unequal sharing of electrons in that very polar bond, but this allows for this molecule to have the polarity. And so what I've drawn by these dashed lines would be what I would consider to be representing dipole-dipole forces of attraction. This is the result of permanent dipoles. So in addition to London dispersion forces, we also have these permanent dipoles and the attraction between the positive side and the negative side. We can do something similar here with our electron density plots, where we could say, well, it's delta negative on this side, and it would be delta positive on this side, and of course there would be the attraction between those portions of the molecule, and so on and so on. These extra attractions add to the strength of the intermolecular forces. So while London dispersion forces are ubiquitous, in a sense they're harder to understand because they're due to temporary dipoles. Dipole-dipole forces will only exist in polar molecules, and therefore they're not quite as common, but they're definitely easier to understand. So now if we come back to question number 4, and if we make a comparison. So let us compare a pentane molecule, 5 carbons, and a second pentane molecule. The only thing that would be holding these molecules together would be London dispersion forces. Okay, so London dispersion forces, and this is the result of temporary dipoles that would be holding these two molecules together. Consider butane-1-ol. So I'm going to draw the 4 carbons, 1, 2, 3, 4, and then the oxygen with its hydrogen. And in a sense here, I am trying to represent the bent structure about that oxygen. So while it looks like it's in 2 dimensions, I am considering the geometry. Now I'm going to draw a second molecule here. In addition to the London dispersion forces that would be holding these molecules together, in particular if you think about the hydrocarbon portion of the molecule, there will be dipole-dipole forces. Now I'm not going to draw the bond dipoles for simplicity, but we can draw a molecular dipole here and a molecular dipole here. And we would expect that there'd be an attraction between the more negative side, which would be on this side, and the more positive side of the second molecule. Of course, this would also be delta positive here, and this would be delta negative here. So in addition to London dispersion forces, we also have dipole-dipole forces of attraction in these alcohol molecules, one to the next. Now, as we're going to see in a minute, this butane 1-ol also has hydrogen bond forces of attraction. But for now, we'll just focus on the dipole-dipole forces. I'd like you to be able to draw molecules, in a sense, draw a pair or a threesome, and to represent how these forces might interact. It's a little bit harder to represent, for instance, the London dispersion forces, in that you're not really sure where to draw the delta positive, delta negative. But in terms of the permanent dipoles, this is actually fairly straightforward. So let us consider then, looking on page 23, where I ask you to engage in such an exercise. So key question number 5, consider the alcohol, the aldehyde, and the amine, and draw a second molecule and highlight the dipole-dipole forces of attraction between these molecules. So I encourage you to turn off the video and give that a try, and then we'll compare answers. Okay, so hopefully you turned off the video and you drew in second molecules for each of these. And the idea is that we want to draw the second molecule so as to highlight the dipole-dipole forces of attraction. So once again, we've got a molecular dipole with this bent structure. So I'm not drawing the bond dipoles, I'm just considering the molecular dipole. And I can perhaps highlight in green that right there, this would be the dipole-dipole force of attraction between the delta positive and the delta negative side. Drawing in the molecular dipole is sufficient to represent which side is delta positive and which side is delta negative. If you also want to draw in the partial charges, that's fine. It just clutters the diagram a little bit. If we now consider the aldehyde, and once again, I'm attempting to highlight the dipole-dipole forces of attraction. And of course, each of these molecules has a molecular dipole in the direction of the oxygen through the carbon double bond oxygen. I'm going to now use my green pen, and we would have this dipole-dipole force of attraction between one aldehyde molecule and the second aldehyde molecule. Okay, so dipole-dipole forces. Finally, I've got an amine represented here. And note, I'm trying to draw this in a sense in 3 dimensions and represent the trigonal pyramidal structure. We do have a molecular dipole in the direction of the nitrogen, sort of pointing it to the top of the pyramid. I'm going to draw in a second molecule here, and I'm going to consider once again the molecular geometry. So if you're asked to do something similar in an assignment or a test, it's important, if it does have 3-dimensional molecular geometries, that you attempt to represent that. Now, actually, I'm just going to draw the second wedge a little bit more to the right so that it doesn't interfere with drawing or attempting to draw the molecular dipole. And now I'm going to draw in the molecular dipole and then use my green pen. And once again, we have dipole-dipole forces of attraction. I will once again remind you that these are all in addition to London dispersion forces. And so it's important, if we want to compare intermolecular forces, that you start with the London dispersion forces and make a statement to what degree you think these are equivalent when comparing one type of molecule to the other. And then consider, well, in addition, what else do we have? Now, both the alcohol and the amine also have hydrogen bonding. So let's explore a little bit what's meant by hydrogen bonding. In the previous chem activity, when I was talking about protic solvents, I actually hinted at the idea that hydrogen bonds are formed when you have a hydrogen connected to a very electronegative element. And among the most electronegative elements, we have fluorine, oxygen, and nitrogen. Now, hydrogen bond is in a sense the strongest of the intermolecular forces, but I want to highlight that I don't think they're necessarily the most important. As I mentioned before, London dispersion forces are ubiquitous. All molecules experience London dispersion forces, and they can be quite strong. But comparing, in a sense, one London dispersion force to one hydrogen bond force, a hydrogen bonding is a stronger force of attraction. And it starts to approach the force of attraction that you'd expect in a chemical bond. Now, let's just highlight the conditions that are necessary to have a hydrogen bond. And I'm going to represent it in this way. So if you have an atom Y and it's covalently bonded to a hydrogen, this is going to be a pretty polar bond if Y is equal to nitrogen, oxygen, or fluorine. So we could say that this is very delta positive, this is very delta negative. And of course, we would definitely have a bond dipole in the direction of Y. So under these very special conditions, you have high polarization of the hydrogen and either the nitrogen, oxygen, and fluorine. Now, if you have this hydrogen in the vicinity of X, now who is X? Well, X is also either a nitrogen, oxygen, or fluorine. Then you have the conditions set up to have a hydrogen bond. So this red dashed line is meant to represent the hydrogen bond. Now, I regret the name for this force of attraction because it's not meant to be a full chemical bond. In part, you can see that in our diagram of water towards the left, this right here is meant to represent the H bond, and you can see that the distance between the oxygen and the hydrogen is on the order of 170 picometers, whereas the actual chemical bond, which is represented right here, so this would be our covalent bond, is on the order of 96 picometers. And so that closer distance between the hydrogen atom and the oxygen atom in the covalent bond indicates a stronger, substantially stronger force of attraction. Now, there's one thing that you can't forget to include, and so I've intentionally left off just for highlight here, that in showing the hydrogen bond, we need to also indicate the lone pair of electrons on X, on that nitrogen, oxygen, and fluorine. So in a sense, it's almost as if that lone pair of electrons is being somewhat shared with that very delta positive hydrogen. And I guess just for completeness, we can also say that this X would be very delta negative. So in chemistry, all attractions are the attractions between plus and negative. So this is a highly specialized, in a sense, dipole-dipole force of attraction because it is a permanent dipole. But it's substantially greater than a typical dipole-dipole force of attraction. We call it hydrogen bonding. It's not a full covalent bond, though. It is one of the intermolecular forces. A very important intermolecular force, however, especially for molecules like water, where water will adopt structures, especially in the solid state, so as to maximize the hydrogen bonding. Of course, then resulting in that great crystalline structure that we know as ice, and ice being in the solid form less dense than the liquid form of water. So sometimes I'll actually ask you to draw molecules in, as I have on this diagram here, and show or highlight the nature of the hydrogen bond. And I always show the dashed lines between the lone pair of electrons on the atom that's equivalent to X and the hydrogen that's covalently bonded to Y. So you can see that there's key question number 6 down here. I'm going to ask you about this question in class, so you can take a preview and then I'll quiz you in class about this. What I'd like to do is run through one example with you found on this next page where we see how we can compare different molecules and to compare their intermolecular forces. I would like you definitely to adopt a certain approach. This is on page 24. And here, in a sense, I'm summarizing the steps to include all of the intermolecular forces and, in a sense, compare properties such as boiling point. So when comparing the boiling points of two compounds or the intermolecular forces of two compounds, it's important that you consider all the factors. Please do not just jump right to hydrogen bonding, for instance. So number 1, you should compare how the molar masses compare. So clearly that's related to the London dispersion forces. And then also how much branching is in each compound. And the idea here is the greater degree of branching, the less linear the molecule is. And therefore the less surface area. Okay, so that greater degree of branching would actually weaken the London dispersion forces. I will remind you, though, that this is always a sort of a secondary thing. First of all, compare the molar masses. If the molar masses are the same, then you consider the degree of branching, which is related to, in an inverse way, to the surface area. You also should look, do we have dipole-dipole forces of attraction, and do we have hydrogen bonding? So as an example, let's look at, under Check Your Understanding number 1, and we're going to compare molecules A and B. They're both ethers, and we're going to compare their intermolecular forces and predict which one would have a higher boiling point. Now, I'm not going to write any sentences here, but in a typical question, I would expect you to prepare a table that I'm about to go through with you, and then write a summary statement. We can practice this a bit in class as well. So the idea is that, one, you're going to want to be comparing the London dispersion forces for these molecules. And in particular, you're going to be comparing those forces that are related, most importantly, to the molar mass, and secondly, to the surface area. Okay, so make sure that you compare both, but understand, of course, the molar mass is the more important. We're also going to be wanting to compare the dipole-dipole forces of attraction. Okay, so I'll write this here. And then finally, you're going to be comparing the hydrogen bonding. So I really encourage you to prepare these summary charts. Definitely, by preparing such summary charts, it organizes your thoughts, communicates to me what you're thinking. But remember, in addition, you should also write some summary statements. Okay, now in terms of molar mass, comparing these molecules A and B, these are constitutional isomers. So I'm not even going to bother to calculate the molar mass. If you want, we can realize that it's 1, 2, 3, 4, 5, 6. So this is C6H14O, and this one is also C6H14O. I can calculate the molar mass, but I know that they're going to be the same because, as I say, they're constitutional isomers. So I'm going to put plus and plus, which indicates that indeed there are London dispersion forces of attraction, molecule A to molecule A and molecule B to molecule B, but they're going to be the same, and so I give them equivalent pluses. The next thing to consider is, do they have equivalent surface area? Now you can see that molecule B is a more linear structure. It has less branching. Therefore, I would expect it to have greater surface area. So we can do something like this. I'm going to put lower surface area and a plus here. Or you can put a bigger plus to indicate greater surface area for molecule B and a smaller plus for A, but somehow make a distinction that there is a difference here. In terms of London dispersion forces, I know that about the ether bond, we do have a dipole, a molecular dipole. And so rather than draw the bond dipoles, I'm simply going to draw these molecular dipoles to indicate that I'd expect that there would be dipole-dipole forces of attraction between one molecule of A and a second molecule of A, and one molecule of B and a second molecule of B. I would argue that essentially they would be about the same dipole-dipole forces of attraction. For the most part, if you have a similar functional group, it would be hard to say that one functional group is having greater dipole-dipole forces of attraction versus another. Now, if you've got two of a particular functional group, of course, that would increase the dipole-dipole force of attraction. Finally, in terms of hydrogen bonding, neither have hydrogen directly attached to a nitrogen, oxygen, or fluorine. So neither have hydrogen bonding. So when you lay out this table here, it becomes pretty clear that molecule B has the additional London dispersion forces because of a greater surface area. So I would expect that molecule B would have a slightly greater boiling point. And so I'm going to, in a sense, highlight this guy, circle him, and say this is the one that would have the higher boiling point. In terms of an answer, I would say something like, while both molecules A and B have the same molar mass, therefore similar London dispersion forces, similar dipole-dipole forces, and neither have hydrogen bonding, Molecule B has slightly greater surface area and therefore would have slightly greater London dispersion forces, therefore would have a higher boiling point. So some statement like that, essentially you're summarizing what is in this table. And so for your own work, you can go ahead and try to prepare tables for these molecules, and I'll quiz you about these parts B and C in class to make sure that you've understand these ideas. Also, what we'll do in class is discuss the relation of intermolecular forces to solubility. I think it's worth discussing these properties in class just to make sure that you're clear on the concepts. So this ends the videos for chem activity number 5, and we have a little bit of work to do in class.